hello everyone. Thanks for your interest. Thanks for coming. So we're going to talk about Quarkus. Who has already tried Quarkus? Any experience? Okay. Well, there is a colleague of mine, so it's good. All right. Well, excellent. I think that everybody should be interested in Quarkus, actually, because I think this is a game changer for Java industry. And I'm going to lay out my arguments. And if after this session you don't believe so, then I didn't do a good job. Okay, so let's try and see. So my name is Alexei. I'm a principal software engineer at Red Hat. A little bit about my professional background. I came to Red Hat from JBoss. There used to be such an application server. Actually, it was probably the first that much successful open source project in Java that made such a splash in the industry and managed to compete with giants such as IBM WebSphere and WebLogic. So as you can see, I joined JBoss. I was pretty lucky. I joined right after the university. And I got right into the EGB2 containers. So I spent a lot of my career working on the EGB containers and things around it. Actually, for most of my career, for like 14 years, I've been working on application servers. And that was pretty much an evolution of the project. So I would start with JBoss 2, JBoss 3, and then it would go to JBoss 5 and Wildfly, you can see, and so on. So now, today, we are talking about Quarkus. And Quarkus is different in this sense because it's not exactly an evolution of the previous technology, like an application server. It's something else. All right? Let me ask you a question. You know, there are games where you are presented with a set of images or objects, and you are asked to identify what doesn't fit. Right? So, if you look at this picture, do you see something that doesn't fit? Or is everything okay? What do you think? Any guesses? Serverless. Okay, right. So, yeah, that's correct. So, not that it's entirely correct, but there is a lot of skepticism and doubts about Java in this context. There are good grounds for that. If Java appeared on the scenes long before Linux containers, right? And the practices of development and deployment of applications were radically different. So what was special about this? You are probably familiar with this way of designing your application. Even though you might have had separation of concerns already in the application, right? Like the 3-tier architecture and all the component-based approach to creating your application. But you would still deploy it as a monolith. You would create an archive, and you would deploy it into some kind of middleware. It says an application server. It could have been a servlet container or something. So that was basically the way to deploy your applications, and it was not uncommon to deploy multiple applications in the same application server. You're probably familiar with this. But let's look at this picture. What is so special about this? So we have an operating system, and then we have a combination of Java virtual machine with an application server. And then we have applications on top of this. So this thing, application server, is a Java process, right? It's a Java process. And the role of the application server is to create an operating environment for the applications to run, right? It's pretty much similar to an operating system. Operating system provides the environment for applications. So an application server is pretty much the same in that regard. It creates an environment to host applications, okay? What is so special about it? This environment is not specific to any application. So me, as an application server developer, I develop my server, right? I have no idea what kind of application will it host. But I have to satisfy any kind of requirement that application may have, right? So I have to be very generic in terms of what I provide, right? So application server developers would include in the application server a lot of features, a lot of services that once you as an end user start using it, everything is there. Everything you need is there. You don't need to have any special step to deploy your application, right? Another thing is, it is a long-running process. So normally, when you start an application server, you start it to run, and it runs for a long time. Well, relatively, but still a long time, like a month or maybe more, right? And once it's running, you can deploy applications, you can undeploy applications, you can start and stop services, you can reconfigure it at runtime. Sometimes you can even apply patches and updates without taking the server down. And that was pretty much common, right? So Java was evolving to support this way of developing and deploying applications. So all this has shaped up Java and the characteristics as we know them today, right? Those were the requirements. And JVM was evolving in that direction. So when JVM starts, it doesn't shy away from acquiring available memory. And we will see an example, right? So when you start a JVM, it will, oh, there is a lot of memory, so I will just grab it because, well, I will need it. Because if you run it in a server mode, then probably you will deploy applications. The interesting thing is, you start an application server, it's an application in Java, right? So it's a process. But when you deploy your applications, you load you load external bytecode into the running process. So that process immediately grows in memory. It starts to consume more memory. More than that, it's a new behavior. It's a behavior that wasn't there when you started the application server. So the process starts to consume more resources, CPU, memory, then it depends, file system, database connections, and so on, all right? So it's just to show the difference, because it's radically different from the microservices, which is the tendency of today. So today, where really more and more applications are architected following the microservices principles. Why? Well, people started to realize that your application performs as well as the slowest component in it. So if you have a large application, it's big, consists of a lot of pieces, and it is monolithic, then its performance will be as good as its slowest piece, right? So now, if you think about it, well, why don't we take that slow piece out of the application and create a separate service? And the main application and that service will communicate, and when that service is not feeling well, let's say under pressure, we create a new instance of that service. So that way you can scale out and improve the situation for your application. Another advantage, of course, in case of microservices, as you can see, you can combine multiple technologies, and they can all work together. They can be orchestrated in as a single system. Okay, that's a great idea, right? So nowadays, we can split our applications or design them as services and deploy them on elastic infrastructure that will be orchestrated in a container. Great. So how about Java? Well, let's look at those applications. Let's look at those services. What does it mean to run as a microservice? We want to be able to scale out. What does it mean? We are scaling out by creating a new instance of a service which is in trouble, let's say, right? So we create a new instance. And what does it mean? We have to boot it. It has to start. So your system needs to react to the amount of, let's say, requests coming in. So the faster the service boots, the better your system will react and adapt to the increased load, right? So if you need to, imagine, you need to scale out, you need to create a new instance of a resource, of a service, and it boots a long time. Well, your system will be adapting to the new load not as quick as you would like it to be. So one of the requirements now, it has to start fast, right, to react better. The other thing is, how many services can you start? If your system scales out by creating new instances, how many instances can you start? How well it will scale? So the less memory the service consumes, the more instances you can create, right? So the potential of scaling out is better if the service consumes less memory. So we have two requirements: fast boot time and low memory footprint. Okay? And ironically, fast boot time and low memory footprint as a requirement, these are two major weaknesses of practically any Java application, right? So if we compare Java in a container to other technologies, Java is not looking competitive at all, right? It consumes a lot of memory. It starts slowly. Even Node.js is faster, and technologies like Go is just, it's completely different level. So if this architecture is the future, then what we as Java developers are going to do about it, right? Should we really start thinking about learning new technologies and abandon Java? I will show you a quick example, because Java in a container and memory. How can we control, or how can we limit the amount of memory consumed by a Java process in general? So let's look at a simple example. Yeah, I will make it bigger. Right. So I have a simple application that I will show you right now. Okay. So this is a simple REST endpoint. Sorry, I cannot see it well even myself from here. So there are two classes, and one is basically the root path. The other one is a path for the REST endpoint. And as you can see, it's listening, and it receives the request and sends a string constant, right? You cannot get any simpler than that. And all right, so I'm going to use a thing called Torntail. We can say that it's a predecessor of Quarkus. The idea of Torntail was to take an application server, strip it down into pieces, and use only the pieces that are relevant for the application. Okay? So it's a kind of already an attempt to optimize an application server for these kind of use cases. So let's run this application. Target. All right, so it's an executable jar. It starts, it's ready. So you can actually see how it works. It is based on Wildfly Core, which is an application server. It boots Wildfly Core in this amount of time, and then it boots everything that's needed for your application. In this case, it's a REST endpoint. Okay, so it took like around, how much? Like, well, let's say 2 seconds, roughly. Let's see how much memory this process, it's an application, how much memory it consumes. Okay. All right, I'll make it once again. So here, the number here is the amount of memory in kilobytes that this process consumes, the application that I just launched. So it's about, well, it's a bit less than 500 megabytes, right? That's quite a lot, isn't it? Well, let's make sure it works, actually. REST. It says, hello from Torntail. So it works. But, okay, it consumes a bit less than 500 megabytes. And that's a lot, really a lot. It's astonishing, right? This application practically does nothing. So if I am a Java developer and I develop this thing and I'm thinking, well, how can I optimize it? And if I open its source code, well, there is nothing to optimize, actually, right? It just returns a string. How can I optimize this? All right, then, being a Java developer, what else can I do? Because I'm not happy about this number. Well, I can limit the heap space. So let's do this. How do we limit the heap space? Well, we use XMX. And I'm giving it here 28 megabytes. Oh, sorry, a white space. All right. So it starts to boot. Now you can see that it boots a lot longer because memory is limited and it's not enough. So garbage collector kicks in, and then you get out of memory exception, which is not a surprise because I knew it would fail. Now I gave it 28. Let's give it 29. And it will start. Why I'm doing this is just to demonstrate that what's the limit for this kind of application. And this kind of application, and based on Torntail, represents a traditional Java application. So it could be a different technology. It could be Spring. It could be something else. But the numbers that you will see here for this application will be pretty much comparable. All right? So with 29 megabytes of heap space, it managed to start. Now you see that Wildfly core started in over a bit more than 2 seconds, while before it would start in a bit less than 1 second. And then there was the rest, right? So overall, it took around 4-5 seconds. OK, but anyway, I mean, the application has started. So that's good. We can verify that it works. I will refresh, and it works. So let's see how much memory it consumes now. The process. Oh, OK. So it now consumes almost 250 megabytes, the process, right? So I just said that I wanted 29 megabytes of heap, 29 megabytes of heap space. But the process consumes 250 megabytes. That's like 10 times more. Well, a bit less, but you get the idea. So how can we control this? So you see the problem, right? So you want to limit the space, but you cannot control the whole memory consumption, which is here. So we as Java developers, we are familiar mostly, right, mostly with this part of the memory, but RSS includes everything that JVM needs. And that is pretty much out of our control. So now, it's even more important in case of serverless, because we want to boot fast, and the process has to consume really little memory. And in case of serverless, you can scale down to 0. And when request arrives, you might have nothing running. So you will have to, when request arrives, you have to boot the service, handle it, and then probably terminate the process. So traditional Java is not usable as you would expect, right? In this case. And of course, if you look at adoption in the serverless area by technology, and given that Java in popularity is language #1, or depending on the survey, is #1, 2, or 3, right? In the serverless adoption, it's really low. It's like 6%. For a good reason. So it's been pretty much negative at this point about Java. But let's be fair. Java is not necessarily slow in general. Java can be pretty fast. And we can see that. We will see that a bit later. Java may actually perform better than a native executable if you give it a little bit of time. So what happens? You start Java, it does everything that it needs to do to boot and initialize services, and then it starts to work. And you know that there is a C2 compiler which can adjust the code at runtime to perform better. And if you give Java a little bit of time, it will start to perform better at runtime. And this is Java's advantage. It's actually pretty fast. It can be pretty fast. Right. So because when you compile an application into a native executable, the compiler does the translation. Here is the bytecode, or here is the source code, right? It translates to this bytecode, and you end up with this bytecode before you launch your application. In case of Java, yes, you translate it to bytecode, but then at runtime, there is a profiling mechanism in the JVM that collects the data and adjusts it on the way, right? So that's the advantage of Java, but it has a cost. And the cost is the memory footprint. Well, that's a nice feature, but it's still sad because it's still not usable in containers. It doesn't really fit well. So, what can be done? I'll stop this application right now. So, the point of this demonstration was to show you that for a simple application, for a simple REST endpoint, what you end up with is 250 megabytes, and you can't really do anything about it. Maybe you can provide some more JVM settings, but you will shave maybe a little bit more, but that's the ballpark of what you're going to end up with. What we can do about this? So we were thinking, because for us, if this is the direction of software development, the evolution of software development and deployment, for us, application server developers, we must do something about it, or we should really also switch to other technologies. So let's think about it. We started to identify the problems, how we can be faster. One of the things in negotiations with JVM people, you may say, well, guys, can you do something about it? You consume too much memory. And the response would be, well, you create a lot of classes. A lot of classes. Maybe we can do something about it. So what happens when we boot an application, traditional Java application? There is an initialization phase. What happens at the initialization phase? At the initialization phase, we read configuration. We analyze annotations. We validate the meta model. Usually we translate the configuration into the meta model, then we validate that it's okay. We load all the classes that are necessary to perform the configuration, such as XML parsers or whatever configuration format that you use. We need to load those parsers, read that configuration, right? The sad part about this, you need these classes, like parsers, only at boot time. When your application is running, most probably you don't need them, but they will remain in memory. They will consume memory until you terminate the process. They will be loaded, but they're not needed. And then there is all other stuff that frameworks do. They create proxies. They analyze classes using reflection and everything, which is slow. And that happens every time you boot an application. And then there is JVM, of course. JVM, when it needs to load a class, it loads the bytecode, it validates the bytecode, and so on. So this is what happens. But in case of deploying into containers, this way of initializing application was pretty much necessary and required in case of application servers, when we had this layer and we would deploy an application. But if we look at containers, the thing about it is the architecture is pretty much immutable. What does it mean? The configuration doesn't change between service starts. So when we're scaling out, we're creating identical instance of a service, which is exactly the same configuration, right? So it's very specific. Right. So it's exact copy. In that sense, it is immutable. And if it is immutable, it opens up the possibilities to optimize the boot. We can try and optimize the boot of an application for a specific configuration. Okay? So if we take an application server which includes a lot of services, a lot of features, we can say, we need to start a service and it requires specific features, so we can eliminate the rest. That's one possibility. The other one, if we could only come up with a way to optimize a specific configuration of an application. And let's think about it. What is a started application? What does it represent? Well, a started application is just a state in memory, isn't it? Well, simply speaking, right? When nothing is running, there is nothing in memory. And when you boot an application, what you end up with is a state in memory, right? So what we need to do is to go from nothing to that state in memory. One way would be to read configuration files and scan for annotations and analyze classes using introspection, create proxies, and so on. Or maybe there is another way. So what we need to do is to cut this initialization phase and come up with something that is a lot more efficient. And basically, this is what Quarkus is about. So if you need to explain to somebody what Quarkus does, you can explain it in simple words. Quarkus creates a fast boot of an application. It makes your boot effective, the most effective, by skipping the traditional initialization phase. How does it do it? Well, we do everything at build time. So there are build plugins, like Maven plugins and Gradle plugins, that you add to your build process, and you compile your application, and then you run a Maven plugin or a Gradle plugin, and we analyze your application, the configuration of your application, and what we output is a bytecode which is necessary to start your application. Basically, a bytecode that allows you to go from nothing to the ready state in the most effective way. Okay. We support a few outcomes. So the outcome of the Quarkus build, you can have an executable for a Java, JVM executable. It could be a thin jar with a bunch of libraries in the lib directory, or a fat jar or an uber jar that contains everything. And another option will be a native executable. So that is the Java application compiled into native executable that you could run. I also mentioned here that there could be possibly other formats. This is relevant for certain deployment models like serverless, so that they require additional artifacts to be able to deploy the service. These are the basic blocks of Quarkus architecture. So there is core, there is GiantX. GiantX is a library that allows to read annotations, class annotations, without loading the bytecode. So you know, if sorry about this, if you need to read annotations, you need to load the bytecode of the class. So, and that is slow. And this is what all the frameworks do, right? So every library now is using annotations. And the worst part is, if you use multiple libraries that scan annotations, every library is scanning practically the whole class path in isolation, so there is no way to share the annotation data between those libraries. So what GiantX does is allows to read annotations without loading the bytecode. So this is a very effective library. There is Gizmo. Gizmo is a bytecode generator, which is used to generate the wiring bytecode for your application. There is an ahead-of-time compiler SDK that we are using to generate the native image. Arc is a dependency injection developed specifically for Quarkus to make it more efficient. And there are multiple extensions that you could use. Extensions, the role of extensions is to provide the Quarkus build process with everything that's needed for optimal boot of an application. So you could say that extensions is what enables using libraries that rely heavily on reflection and all the other things to boot effectively and work in both JVM and native mode. So every extension is split in two parts. There is a runtime part and a deployment part. So normally, when you develop an application, you would depend on, let's say, Undertow or Hibernate or something else. You would depend on the jar, which represents the runtime dependency. And we, at build time, we would figure out what is necessary to process your application, and we would figure out the other part that contains the optimal boot for this specific library. Okay. And this is how the process looks like, the build process. So you compile your application. You basically do Maven clean package or whatever. Then Quarkus receives the bytecode here. We analyze it. We process dependencies. We generate the optimal bytecode to start your application, and then we produce the output that you requested. It could be a JVM executable, a native executable, or maybe some other thing. So nice theory, but let's look how it works. I'm going to now generate an equivalent application that we just saw, the same REST point. And we will compare the boot time and memory footprint. So I'm going to generate it using a Maven plugin. So this is one of the ways to create an initial project for Quarkus. Create, and then it is asking me for group and artifact ID, which I will use Devoxx. Then it is asking me whether I want a simple REST resource. I will say yes. It will ask me the class name for it. I will use the default and the path. OK, it's done. So I will import this project into the IDE, and you will see that it is pretty much the same as the previous application. OK. It consists of one class. I will make it bigger. So as you can see, it is pretty much the same. It is returning a string. All right, so let's build it. Maven package. Oh, sorry, I'm not in the right directory. Maven package. Okay. All right, so if I go to the, well, let's see what it generated. Or rather, yeah, okay. So this is the target directory. As you can see, the first jar here is the usual jar. It's the one that you would get if you just simply compiled your application. And the other one, as you can see, it has a runner jar. So this is what Quarkus generated. And there is a lib directory, which contains all the libraries that are needed at runtime of your application. Let's run this application. Java jar target hello runner. All right, so first of all, you can notice how fast it started. It started in, where is it? Running started in, well, a little bit more, but roughly half a second. Let's see how much memory it consumes. Hello. All right, so it consumes 120 megabytes. As you can see, that's quite an improvement, right? This is the whole process. So the equivalent, notice that I didn't specify any constraints, no XMS, XMX. So it's running the same way as the first one, which is here, which consumed almost 500, right? So this is unconstrained, and it consumes 120 megabytes. Well, let's see if it works, actually, right? That's not the one. That's not the one. Okay. Hello. And it says hello. Okay, so it works. Well, let's see if we apply some constraints. You remember that the lowest heap for the previous application was 29 megabytes. Okay? And 28 would throw out an exception. So let's see how much should I give it? Let's say 5. XMX 5. Okay, not enough. Let's see if 7 is enough. Ah, sorry, right. Thank you. Yeah. So 7 is enough, and it boots in approximately. So remember that when I limited the memory, it would boot like 2 times slower. So we get, well, roughly the same. It's 106, right? Milliseconds. Where is it? It's here, right? So it's 0.67 if we really want. Actually, let's see what's the limit. Would it work with 5? It works with 5. Okay, so now let's see how much memory it consumes. All right, so 60 megabytes. That's not bad, isn't it? It's much better, at least. So previously, this was the limit for an equivalent application, and it would consume 250. And now with Quarkus, it consumes 63. And it is the same JVM. I haven't changed it, right? It is the same Java virtual machine that was running this application is used for this one, and it consumes a lot less. And the application is practically identical. right? It's just a different string, but it is the same. All right. So now, if you think this is it, this is actually the starting point. So let's go back to the presentation. Now, we are really going to go super tiny and super fast. Sorry. If we continue this thought that in the container is immutable and the environment is the same, right? It's not like we compiled Java application and we should be able to run everywhere, who knows which operating system. When we are running in a container, usually it's a Linux container, right? So we know it's a Linux container. And the configuration doesn't change. Practically, environment doesn't change. So why don't we try and compile it to native? Right. So there is, however, a problem with this, potentially. Java is a dynamic language. Dynamic in which sense? In Java culture and design patterns and practices, a lot of it is based on resolving things at runtime. All the inversion of control, dependency injection, introspection, all that by design happens at runtime. And that is kind of a problem for a static compiler, because when you start a Java application that uses all those indirection, the resolution of all this can only happen at runtime, because this is where we analyze what's available, which implementation to use. We can only do it at runtime, normally. So there is a hard problem, because the static compiler, you cannot perform a static analysis until you run your application, right? This is a major problem. In some cases, you could, but it's not easy. And there are cases where the static compiler will just fail because it doesn't know what to wire, what to inject in your field, right? That's the problem. And this is where Quarkus helps a lot. So Quarkus facilitates generating the optimal code. So the most effective code is, at runtime, is the simple code. Let's say the direct procedural instructions are most effective, right? Because they are straightforward. There is no indirection, nothing to figure out which implementation to use, and so on. So what Quarkus does here, it attempts to streamline all the configurations, all those indirections, and produce the bytecode that is easy to analyze for a static compiler. And this is the differentiator of Quarkus, because you will see that a lot of libraries and frameworks will try and create a way to generate a static image. You will see that. It's already happening. So the differentiator of Quarkus is that it helps to produce a code which is easy for static analysis, and it's the most effective. Because it doesn't mean, so if you have an application, a Java application, well, there is a static compiler. We know that static compilers exist, right? So why not apply a static compiler to your application as it is? Why do you need Quarkus for this? The reason is that the original bytecode is not easy to translate. And even if it manages to do this, the bytecode that will be generated will not be as effective as the bytecode that Quarkus generated. So Quarkus was originally designed to produce the effective bytecode that will be easily translated into the native image. It doesn't mean that it is specialized for this. As I showed you, this application in Java, it's a pure Java application, and you can run it as a Java application. There is nothing wrong with this. Quarkus simply gives you an option to produce an effective native image out of that. However, there are certain limitations. So when I talked about in the beginning about the application servers and how we deploy the applications and the ability to load the bytecode at runtime, Java was all about that, and it's really powerful and cool. But when we're talking about generating a native executable, we can't really support dynamic class loading anymore, right? Once you generated the static image, you cannot load Java bytecode into it because you need a JVM for this. But I think it's kind of natural, but still it's an obvious limitation. Dynamic class load. So if your application is based on dynamic class loading, you cannot generate a native image for it. As a consequence, there is no need for security manager. Since we are not loading external bytecode, there is nothing to verify, so we can just skip that. Finalizers are not supported, but they have been deprecated for quite a long time, so you probably don't need to use them. The kind of sad thing about it, you cannot attach agents or debuggers to a native image because, well, that's a different world, and the debuggers are based on JVM, and that's a different executable. How about reflection, dynamic proxies, and other Java features that a lot of frameworks actually use? So reflection, dynamic proxies are the examples of those indirections, right, in Java that are difficult for analyzing in a static compiler. So that is possible, but you need to provide a list. So if you run a static compiler yourself for your application that uses Hibernate or dependency injection or something else, you will have to provide a list of classes, your entities or other classes that are used for dependency injection, to the static compiler to say, well, these are the classes that are using reflection, so please take care of it. If you don't do it, the static compiler will be confused and simply give up. Okay? So in case of Quarkus, you don't have to do this because Quarkus analyzes this for yourself. So if you are using Hibernate, at build time, we see the annotations, we see the configuration, and we can see, okay, these classes need reflection, so we will take care of it. We will simply collect all this information about proxying and classes that require reflection and give it to the static compiler transparently. So you will not have to do anything. You simply do Maven package, and that's it. Everything as usual. And the other most interesting thing is when we build a native executable, we may say that, well, there is a notion of a closed world. Closed world means you compiled your application, and it's self-contained. Right? It contains everything that it needs at runtime. It has some dependencies on libraries, but that is it. Your code, your jar file, and external libraries listed as your dependencies in your project. And that set is complete. You will not need anything at runtime. So now we say, OK, nothing else is needed. So what the static compiler can do now is actually analyze what's used. Because at the end, we need to produce a native executable, so the static compiler has a chance to select the bytecode for that native executable. What it means is, well, in Java culture, usually, when we are developing an application, we use utility classes. There are all sorts of utility libraries, and you've probably done it yourself quite a lot. You need a few utility classes, they are in a library, so you add a dependency on that library, right? And actually, you need just a couple of classes from that library, but you added the whole library as your dependency, which may contain 100 or 200 or 300 classes. So when you are generating a Java executable, all those libraries are listed as your dependencies. But when we are producing a native image, the static compiler can analyze what you actually use, what is actually required, and it can see that, in your application, you reference only those classes. So it says, I'll take only those classes and put them into the native executable, and the rest of the library I will not touch. Okay? So this is really, really effective. And the same happens even to the JVM. So when you start your Java process, there is a runtime, Java runtime. How much % of Java runtime do you need at runtime? Well, most certainly not all of it, right? So what static compiler does, it analyzes your application, it performs, it does it to a field level. So even if you have a class and you don't use certain fields, those fields that are not used will not be there. So there, in the native image will contain only the fields and only the methods that are actually necessary at runtime. And that will apply even to the JVM native classes. Okay? This is very, very cool. So let's see it in action. Again, nice theory. Let's see how it works. So I will now build a native image. Am I in the right directory? Yes. Clean package. I'll skip the tests. Skip ITs. And what I need to do to build a native image? Sorry, it's. If you can see, I'll clear it. Skip tests. To build a native image, you just need to say dnative. What dnative will do is it will activate a native profile and will start a native build. So the downside of native build, it takes a bit of time. It has to, at least right now, it will take a certain amount of time. We could say it's long. Even for this simple application, as you can see, it's working hard. Right. If you have any questions, feel free to ask until it's building. It's finishing. Yes?
Does that native build actually use, is it GraalVM?
Yes, we use Substrate VM for this, yes, at this point. But what Quarkus does, first we build the Java bytecode, and then we use a static compiler. So when we build this bytecode, it's a bytecode that is in general easy for a static compiler to analyze. So if there is another alternative, it doesn't mean that Quarkus will not be as effective. So what Quarkus does, it enables static analysis of a Java application in principle to build the, in principle, effective native image. All right, so what is it called?
Sorry, one more question. Do you know if any of this cool stuff applies to the Scala world?
To what? Sorry?
Scala.
Scala. Right. So we do have a. So I mentioned before that we had extensions, Quarkus extensions, and those extensions are exactly what they're kind of adapters of a technology to support building applications in native images. And we do have an extension for Scala and Kotlin as well. In fact, I'm not sure whether there was a presentation. Actually, there was a practical class at Devoxx. I'm not sure whether it was today or yesterday, about Kotlin in Quarkus. So we have the same extension for Scala. Yeah. So.
Okay, thanks. That's cool.
Great. All right, so let's run it now. This is the same application. Oh, let me just. Okay. So where is the number? Started in 5 milliseconds. 5 milliseconds. It's the same application that a traditional Java application would take a few seconds to start. This application in native image will take just 5 milliseconds. Let's see how much memory it consumes. It consumes, well, 20 megabytes. All right. Well, you could say that, well, this application does nothing really, right? It does nothing. It's not. It doesn't mean that your full-blown application will start in 5 milliseconds. Of course not. But I mean, application does nothing. It should start in no time, isn't it? It shouldn't take seconds to start a nothing application, right? So that's already something. Well, we could play a little bit and see that, you know, that in this case, a native image, it produces a native image, but there is still a garbage collector in there. It's a simplified one, but it still exists. And there is still a notion of a heap space. A question? A size of this binary, let's see. The size of this binary is this. So it's, yeah, you can see. All right. It's mostly for fun. We could say it still supports a heap space with XMS and XMX. So how much do you think we should give? 1? Well, let's give it 1. 1 in. Right. And it still works. Well, you can notice that it doesn't start in 5 milliseconds now. Where is the number? It's 100. Well, you could probably, yeah, it's, I'm not sure you can see it, but whatever you want. Sure, let's do it. So I am refreshing now. Oh. Oh, it broke. Great. But actually, to your point, what does it make sense? Let's see. I will start it again. And let's see how much memory it consumes. Well, it's pretty much the same, right? So you don't really gain by going that extreme. So we could say that it doesn't really make sense to use that low of a heap space. It's interesting. Let me refresh again. No, it really does work. Let's see if 2 works. OK, 2 works. All right. OK. So this is just an illustration. I just showed it to you, but this is just in comparison. So the numbers that I showed you were slightly more here and slightly less here. So it depends really on your system and how many cores you have. But roughly it's the same, right? So as you can see, this is for simple REST, right? If you look at, if you make it more complex, so if you add a Hibernate, let's say a JPA to your application, this is how the picture will look like. Yeah, well, you can see that. The RSS with Quarkus in JVM mode will be around 2 times less, and with the native image, as you can see, it's a lot less. And the time to first request. So I could call it a boot time, but boot time is, in different frameworks, it means different things. Why? Because some frameworks want to show you a good boot time by booting, but not everything. Something will be initialized on request lazily, and they call it boot time, so they boot, and then when request comes in, they start to initialize the services that are necessary to handle the request. So in this case, we're not cheating, right? So this is actually the time to first request. There is no lazy initialization. What you saw here is not lazy initialization. We initialize all the services during the boot. And this is the difference. So with the traditional stack, you can see you can get to 4 seconds, Quarkus, JVM, and native. And you can see the difference. OK. Any questions so far? Yes. Here's the answer. There will be a section. So I anticipated your question. Now I'm going to talk about it in detail. OK? Yes, so this is a very natural question. Now we have a Quarkus enables you 2 options. You can compile your application into Java, make a JVM executable, and you can have a native executable. What to choose? It's not really obvious. So we did some performance tests to help you. It really depends. The answer to this, when people ask, so what should I prefer for production? And the answer will be, it depends. You have to try it and see how it works. And you may have different requirements. So here is an idea for you guys. So we performed a test with 40 concurrent connections and a single thread. And we are comparing the same application. Well, it's not only REST. It was reading data from a Postgres SQL. OK? In comparison, Torntail, Quarkus JVM, and Quarkus native. So the interesting thing in throughput measured in requests per second. So with 40 concurrent connections, Quarkus native image would perform practically 40% better in terms of throughput, because what is performance, really? Performance is context specific. It could be boot time, it could be throughput, it could be memory consumption. So it's really context specific. So in this case, about throughput, as you can see, JVM actually is the champion in terms of throughput. Why? Because JVM adapts at runtime. It performs optimizations of the bytecode at runtime, and the throughput is apparently better than the native executable, right? If you run your application with a single thread and 40 connections. However, it comes at a price. If you look at RSS, which is the memory consumption of the process, you can see that Quarkus native image is here, and Quarkus JVM used almost 300% more memory than the native image. So it comes at a price. Here is the throughput as a function. Yes?
Sorry for interruption. Could you please go back to the slide? I have a question in regards how do you compile this native image? Did you play with hyperparameters like more aggressively inline everything, etc., or that's just default Graal compiler parameters? Because there are in Graal, there are a lot of improvements if you play with compiler parameters.
Oh, okay. Do you mean that?
For instance,
Graal allows you to
more aggressive inlining, for instance.
So, to be honest, I will not be able to answer this question in detail, but I can provide this information to you. Just need to look it up. But what is true about the native image generation? When I was saying that when you use ahead-of-time compilation and you produce native binary, and the static compiler doesn't know how the runtime, how the application will perform. So what will be used the most? Which bytecode will be used the most at runtime? So if we are talking about Graal, Graal allows you to collect that data. So you can take your Java application and attach a kind of, do a series of runs with Graal to collect the profiling data of your Java application. And then when you generate the native image, you can provide that collected data to the static compiler, and it will take it into account when generating the native image. That is true. That is true. However, the difficulty is to really imitate really well the load that you are generating and make it close to what the actual load will be at runtime. Okay, so here is how the throughput looks as a function when the concurrent users increase. You can see the JVM is on the top, which is the higher the better, right? So the traditional Java with torn tail is the lowest one. So as you can see, you can see, right? This is thousands of requests per second. This is how it looks like. But, okay, so that was one thread. But if we deploy in containers, so with this, what does it mean? Should we use Java? Well, in this case, yes. But if we are deploying in containers, Java consumes a lot of memory. And for that amount of memory that Java consumes, we can just launch many more instances of native executables. So if we use containers limited to this amount of RAM, here's how it looks like. If we use all that memory, dedicate all that memory to the applications, you can see that with the native executable, well, you can see it can be that much faster, right? I mean, in throughput. which looks very impressive. How about the response times? So that was throughput, which is a number of served requests per second. How about the response time? The response time is the amount of time from the moment request was sent to the moment response was received. Response time. There is the mean response time and the maximum response time. And here you can see that, again, the Quarkus and GraalVM mode shows better results. In native image, actually, the mean response time is not looking really good comparing to other. That's in milliseconds, right? So it's not a huge time. But if we are really comparing this, we can see that, OK, that's what we get. And then the maximum. You can see the maximum as well. So why is this happening? What's happening with the native image? Well, apparently, it's at least it looks like that the garbage collector in the native image is not working as well as in the JVM. And this is what makes the difference, right? However, when we're talking about the maximum response time, the native image performs super stable. In Java, it's it's not as stable. It really depends how it works. But in the native image, it shows a really stable result. And here is as a function of increasing users. All right. Do you have any questions about this so far? Yes. Sorry, I cannot hear.
How much minimum memory will be allocated for new threads in native image?
The minimal memory for a native image?
Yeah, for a new thread. Usually in Java you have 1 megabyte in Java 8. And
sorry, I don't really understand the question. The minimum amount of memory for
one
a native
thread.
Image for one thread.
Yeah, when you create
in this test, because it really will depend on your application, right? What it does. So I'm not sure how to answer your question.
Usually
just in general.
The OS allocate memory for the stack of one thread or one process. In Java, it's, I think, 1 megabyte for one thread. Or 10 threads, you have 10 megabytes, but I'm not sure when you compile what kind of memory will allocate for this new thread.
What does the application do? I'm misunderstanding your question, or
I mean, if there is any difference in threads when you have a compiled version or a GVM version. If you have 10 threads in GVM version of the application, and then what's the difference between native and the GVM version of Quarkus in memory?
But it will still depend on the application, right? It's not about the threads. It's how the application behaves, what it does, right?
If you just
default
allocate
values,
the thread without doing nothing.
Default values for new threads. Recommended default values, or?
I think in Java it's 1 megabyte per stack.
You want to know the same in the native image?
Yeah, if it's there, any improvement there.
I don't know. I really don't know that. Okay. All right, so that was pretty much the technical part, right? Now, well, let's see what it's like to develop applications with Quarkus. So in Quarkus, we are, first of all, what our goal is to not come up with a new development model. So if you know some APIs, you're used to using some libraries. We want to make sure that you still can use those libraries and you kind of feel at home when you're developing with Quarkus. So we support all the APIs that you are used to: Hibernate, JPA, and web containers, REST, and so on. Right? So this is our goal, to make it, you don't need to learn anything special about it. In Quarkus, we are trying to promote and be standards-based. So we are really trying to promote the microprofile and the Jakarta API, but it's not limited to that. So you can still use libraries, proprietary API, and annotations, and etc. We use a single configuration file. Usually it's a unified configuration file. So it's not like in an application server where you have configurations spread in multiple places, a lot of XML files. We're unifying that all in one configuration file, which I will show it to you a little bit later. And one of the features is, since Quarkus is so fast, it boots so fast, it opens new possibilities for development. So we support a so-called live reload. If you haven't seen it yet, have you attended Edson's Quarkus live coding presentation? So if not everybody, I will show you some of it. So if I go back to this application, this hello application that I demonstrated before, I'll go back to it. So before I was starting it as a jar or as a native executable, but there is another option. We call it the dev mode. I can start this application in dev mode by saying Maven Quarkus dev. So Quarkus, in this case, is an alias for the Quarkus Maven plugin. So I start this application. It started. I'll make sure that it works. I'm reloading it. It works. All right. So what I can do now, I can go back to my IDE and say, well, I could say, hello, everybody. And I save my Java class. I go back to my browser, and I refresh, and I get the changes reflected immediately. Okay? So normally, you know, with Java, you have to, if you make changes, you save them, you recompile, you rebuild your application, then you restart your application. With Quarkus, you can just edit your source files, save them, and see the result immediately without going to Maven, clean, compile, or package, and everything. So we could do more than that. We could say string greeting, and we say config property. This annotation, config property, comes from the microprofile, and I will give it a name. Greeting. I'll say greeting. All right. Now if I go back and refresh the browser, I will get an error. And the cool thing about it, well, errors happen, right? When you develop something, you forgot something, you made a mistake, and it may not compile or something like this. So this is just to illustrate what happens in dev mode when you make a mistake. It shows you an exception explaining what went wrong. So I was trying to use a property here. I wanted to inject a property called greeting into this field and display it here. But I did not define this property anywhere, so it failed. It says no config value of type string exists for greeting, so let's fix it. I go back to my IDE. I find my application properties, and I say greeting equals, well, let me try and impress you with my blind typing. Repeat. Any idea what I wrote? I save it. I have no idea what I wrote actually. So, private. Oh, see, I got it right. So that shows you that when we are not only monitoring the Java classes, we are also monitoring the resource files. So if I change my properties, you can see that they are also picked up and displayed immediately in the web browser. Well, I'll make it a little bit more complicated. I can say, I can create a bin. I could say it greeting formatter. Let's say, I say it's, oh, sorry, application scoped. This annotation is useful when I want to inject a bin in one of my classes. So I will say inject greeting formatter greeting JavaX inject, and I can say, oh, I haven't defined any methods, so here I could say string message. Actually, let me say optional string name. Property name. Config property, yes. Greeting name. All right. And finally, I'm defining my format method, which will return message plus. Here, name is optional, so it means that name might not exist. So I'm using this as name or else. I will say on. All right. Now if I go back to my file and I modify it and say message hello reading format. All right, let's see if it works. All right, so it says hello there. So now, as you can see, I defined my bin. I wired properties to the fields of that bin, and I injected it into my resource, and it kind of worked. What else? If you look at this application, by the way, when I start the application, I showed you hello REST endpoint. If I go to the root, you will see this page. And this page, this is an index.html page. It was also generated for your application, and you can find it in meta-inf resources. This is the default page. You can see it in my IDE. All right, what I wanted to show you as well. Okay, so the project that was generated also included test classes. You can see the test class. This is how the test classes look like. We are using REST Assured, which is a library that allows us to test REST endpoints in a simple Java class, so you can see we are getting response from hello, and we're expecting hello. You can run them from your IDE. So you can just, right? It starts Quarkus, and it failed. It failed because it expects hello, but to fix it, I would need to do print. Oh. Now if I restart it, now it works. Another thing that I wanted to show you, sometimes when you develop applications and you test them, you may want to have different configuration profiles, right? So there could be, let's call it production profile with settings for production environment, and there could be test-specific ones, right? So in Quarkus, there are 3 default profiles. So if I say here, by the way, I didn't specify the name here, so I could do it as well. But anyway, I'll show you it probably later. So if you want to define a property in a different profile, you would use % and then test. And then you could say greeting, message, and you could say hello. No, sorry. Hello. So now if I run my test, it will fail because for test profile, I redefine this property as hello. Right, so I need to adjust my test. And I'm expecting here hello. Rerun my test. Why not? Okay, right. So let me, because it adds the value of the name, so I'll just say greeting name will equal there. And then it will look like there should be this. Okay, it passed, but if I reload my page, hello, it will still say privit one. Okay. So that's kind of you can define your own profiles as well. So here's an example. You can name them the way you want. You can say, let's say, Devoxx, greeting, message, and then, well, I can say bonjour. Right. Devoxx. Okay. A moment. If I want to run a specific profile, I would do it. I would say clean package. Okay, I'll do this. Now to activate a profile, clear Java, jar, target, hello, runner. There is a property called Quarkus profile. I see, profile Devoxx. All right, if I go and refresh the page, it didn't work. Why didn't it work? Quarkus profile. Sorry, it's no. It's wrong place. So I have to put it here. Quarkus profile Devoxx. right? Okay. All right. So this is how you can use profiles if you find it useful. So a few words about, so we are 35 minutes. The interesting thing about, I want to say a few words about the configuration file. So Quarkus generated this configuration file for us, application properties. But naturally, there are much more properties than are listed. So it generated without any properties, but there are properties that you can use. For example, you can change the port, right? But where to go to find all those properties? What is supported? There is a command called Maven Quarkus. I think it's called generate config. Let's see if it's right. So this command generates, in this case, it generated application properties example. There is an option to provide a name of the file, so you can actually generate application properties instead of an example. And this file is going to be, I need to refresh probably. Yes. It's a file that contains all the properties for your applications commented out with the explanations what they affect. So if you want to see the properties that you can use for your application, you can generate this file or take it as an example and go and modify them. And this file which is generated is specific to your application. It doesn't include all the properties, all the possible properties. Why? Because it really depends on what you are using. For example, if I go to the POM of this application, this is what it generates, by the way. So it uses Quarkus BOM, which is the management section, dependency management section of your application. Then you can see Quarkus REST Easy and a couple of test dependencies. So what you're using from Quarkus is basically one extension, Quarkus REST Easy. Well, it depends on a few others, but this is what you specify in your application. It looks pretty simple. There is the Quarkus Maven plugin. It hooks into the build and produces this optimized Java binary. You can. No, that's not the dev mode. This is not the dev mode. This is a part of the build. This is part of the build because Quarkus produces the bytecode which is effective, right? Effective to start. It's not a traditional way because if you don't have this step, you will build an application which is Torntail-like. It will be initializing at runtime. So what this thing does, it moves initialization to build time of an application, right? So why this application starts so fast? Because we are not processing any configuration when we boot the application, right? Then there is the native profile, which enables generation of the native image. And as you can see, there are tests supported for native image as well. All right. So as you can see, what I wanted to show you is the generated application properties example includes configuration options that are relevant for this configuration. So if I look here, if I just less source main resources example, and I try to list, let's say, Hibernate configuration options, they're not there because my application doesn't use Hibernate. But if I add an extension, here is how I can add an extension to my POM file. One way would be to just go in the POM and write dependency, group ID, and the rest. An alternative way would be Maven Quarkus add dependency sys, no, add extensions, then d extensions, and here I can say which extensions I want. Hibernate ORM, let's say. So here it shows it added these extensions to my POM. So if I look at my POM now, you can see that it added an extension. You could have added it manually. There is nothing wrong with this, but it's kind of convenient way. And now, if I generate the configuration the same way, generate config, and I look for Hibernate properties in it, I will see a bunch of Hibernate properties in that file. Why? Because now we see, oh, we are using Hibernate, so we need to add Hibernate configuration properties to that file. They're commented out, but it helps to see what they are and what you can do, what you can configure there.
Sorry, I have.
Yeah.
I have a question. Whether it's possible to use YAML for configuration files?
Not right now.
Okay.
No, we are using properties. Okay. Okay. So as you just seen that I added Hibernate by just typing Hibernate ORM, but how do I know which extensions are available and what are they called? Actually, here, when I did this, okay. How to see which extensions are available? There is a command called list extensions, which will list all the extensions that you can select here. So this is kind of a programmatic way of doing this. You can also have a bit of a nicer interface if you go to a website called Code Quarkus.io. You cannot really see it there. I'm not sure whether I can make it bigger, but it's called Code Quarkus.io, and here yeah, you could simply, this is an interface to generate, so you can provide group and artifact ID for the applications that you are creating. Package name, why is it so? Okay. And below here, you can see a bunch of extensions, and you can simply go and select what you want. Kafka, client, and the rest. Eclipse, Vertex, Smallrye Health, and Kubernetes, and so on. You can see they're listed here. You can also search for the extensions. You can say, what can I say? What can I say? I could say, well, okay, I'll go again to Hibernate. If I start to type, you can see it shows me what's available here. So I'll go a little bit up. Right. Okay, so you can select whatever you want. And then when you are done, you're simply going to generate your application. And it packages it up and downloads it here. And if I unpack it, it will be exactly what I wanted. So you can see the project, source code, POM, and so on. All right. Also, we are claiming that we are native, tailored to native, cloud-native applications, right? So there are also a couple of Docker files that are generated. They are not shown in the IDE, but I will, by the way, remove Hibernate from here for now. Okay. So what I could do now, I want to, for example, if I want to create a Docker image for my application, so I will just do that. I will say Maven clean package d native to activate the native profile, and then I will say d Quarkus native container build. True. Right. So now it is going to generate a native executable to run in a container. What's the difference? So as you can see, the command that is building the native executable is a docker run and the rest to generate a native executable to run in a Linux container. So for my machine, it doesn't really make any difference because I have a Linux installed. But if you use a Mac, when you say Maven clean package D native, it will generate a native executable for Mac. And you will run it as a native executable on your Mac. But it will not run in the Docker container, which is a Linux container. So this way, if you generate it with Quarkus native container build true, it will generate a Linux executable on your Mac machine, right? You will not be able to run it on your Mac as it is, but you will be able to run it in Docker. That's the difference. So now I could say Docker build file source main docker native, I think. T Quarkus hello Devoxx UA. All right, it builds the container. Docker run what's the command? Sorry. Less. Readme. Yes. RMP 8080. And then hello Devoxx UA. Is that correct? No. Quarkus, right? All right. So this now I started this application in Docker, and you can see it still starts in 5 milliseconds. Oh, we can see that it works. It works. All right. Yes. Sorry, could you please repeat?
Okay.
Yeah.
So the dependencies, you have added vertex, but the artifacts related to the Quarkus, I mean, the feature of or thing. Let's say I want to add another dependency to my code, like maybe Apache Commons, maybe RX Java or some that kind of stuff. What is the impact of this?
They will be used for your application. You control what's used for your application.
In that case, why did you add, can you actually show the POM again vertex? Why didn't you add the native vertex artifact to the your code instead of, it says special version of the vertex, I guess, right?
Yes, yes. The same for Hibernate, actually. Did you see? I added Hibernate ORM, and it said Quarkus Hibernate.
Yeah, exactly.
Not exactly Hibernate. The thing is this, you can use it, really. In JVM mode, you can use it. You can use, in JVM mode, you can use anything, no restriction. But you lose the, what Quarkus does, this effective boot time. Because if you use Vertex or Hibernate, the original binaries, when you boot your application, what Hibernate does, it reads configuration files. It scans the class path for annotations, processes them, performs bytecode manipulations, right? And this will happen at boot time, when you boot your application. So when you say Quarkus Hibernate is a Quarkus Hibernate extension. It depends on Hibernate, but at build time, it says, I know how to adapt Hibernate to boot effectively. See? That's the difference. This is what makes it boot faster. So you could use Hibernate, but you would probably see a different boot time. That's the difference, yes. Oh, sorry, I will not hear you.
How about Spring framework? Can we use it?
How?
Spring.
Spring?
Yeah.
Yeah?
Can we use it?
Can you use it in Quarkus?
Yes, yes.
No, you cannot use Spring in Quarkus, but we do have a compatibility layer, which means we support, I have to check what exactly. So we support Spring data annotations, and yeah, we'll need to check. You can, actually, let me just quickly check. You can, if you want to see what's supported, you can also go to the website, quarkus.io. You can go to the guides. Let me see if I can find it. Okay, I'll make it bigger. So see, I found the answer to your question. Spring compatibility. So if you are using Spring annotations, you can use these kind of annotations in Quarkus. So it's not, we are not running Spring in Quarkus, but we will recognize those annotations and they will work. You can see DI, dependency injection, web, and data JPA API. Okay. So that will work. Yeah. So this is meant like, this is not meant, it's not exactly a migration of your application as in the sense that you take your Spring application and build it with Quarkus, but it really helps you start. If you like to develop applications with Quarkus and you are used to using Spring annotations, that's one of the ways to start quicker, let's say, yes.
The question is, for me, maybe I missed that point, but what is the default application server you use? And is that startup time is because of application server? I mean, is this code application server specific? If I will switch from one to another?
Okay. Well, there is no default application server. There is no application server. There is really no application server. Yes. So there could be a web server, but there is no web server unless you add it yourself. So. Okay, if your question is web server in terms of servlet container, well, you could use Undertow, but it's not included in the example. So if you want to use Undertow, you would say Maven Quarkus add extension, D extensions, Undertow. If you use a servlet container, you could do this. Now you see that extension Undertow added. So when you build your application, the Undertow will be a part of your application. Vertex. So that was the default. Originally we used Undertow, but then to make it more efficient, and especially for serverless and Lambda and Lambda functions, we realized that we really need to get rid of the servlet as a default. So we switched to Vertex. Okay.
One more, sorry. What is the trick with this live reload? So, because it's actually interesting stuff.
Yeah, good question. So what happens? So actually, yes, what happens when we do the live reload? Well, there is no trick, really. We completely rebuild the application and restart it. But because Quarkus is so fast, you just don't notice it. we are looking for changes to Java files on the disk. And then when we receive a request, so there is a part which is listening for incoming requests. We receive a request. At this point, we check, have there been any changes to the source files? If there were, we recompile them, we rebuild the application, and we put out the response. And that happens like this.
So what does that actually? Like?
Well, there is a part which is listening for the request, okay? When request comes in, we receive the request. And then we say, okay, let's check for changes. If there were changes, we rebuild the application, we restart it in the background, we send the request to that application, it handles it, and so we intercept the original request. Yeah? Okay. Yeah? To switch to what?
Analyzes whether something has changed. So in production, I don't know this. I don't want this logic.
Well, but it's a dev mode. It's not. Look, you have to launch an application in the dev mode for that to work, right? So you enable it when you launch it, right? Of course, this is not for production. It's not going to work. Yes, other questions?
Some platform-dependent libraries like Azure SDK are in plans to adopt it for Quarkus.
Yes. So first of all, you can use Quarkus to build Java applications, not specifically for a container. It's Java executable. As you can see, most of the examples were not running in a container. So you could use it just like this, right? About the Azure, again, we do support Azure and Lambda. So if you go to this website, let's say, you can look for deploying to Microsoft Azure. Azure functions with Vertex and so on. So we do support that. And it's a little bit, the project setup is a little bit different because you need to produce additional artifacts to be able to deploy. And it explains how to do this. For now, we are doing this with Maven archetypes to generate the project and produce those artifacts. I could say that we will definitely be improving developer experience for Azure. So it is supported. You can read how to do it in a guide. We don't have really much time now. The same for Lambda, Amazon Lambda. But yeah, this is, yeah. I hope I answered your question. Yeah? More or less? Or?
About read and write in blobs and
reading and writing blobs to what?
to Azure.
To Azure.
It has special functionality to store in big data into text files, which is called blobs, and it's really time-consuming to work with it. So,
all right. Well,
it was just a general question. If you are going to extend the number of your extensions according to the working to platform.
All right. So the answer to this is definitely yes, because yes, that's our purpose of Quarkus. We want Java to be working well in serverless. So we are definitely going to add support for more extensions and so on. So absolutely yes. The answer to this is yes. So if you ask me like right now how to do it right now, I will probably not really be able to do it right now, but yes, the answer is definitely yes. This is the priority for us to make it possible.
Thank you.
So, you're welcome. Yeah, I guess, well, yeah, I guess that's it. Do you have any more questions? Yes.
So those extensions you showed on, let's say, code.quarkus.io, so they all support like GVM mode as well as native mode,
Yes.
all of them. Right.
Okay, the situation right now is this. By the way, I was using Quarkus, well, that will not tell you anything, 0.27.0. So we are approaching the first officially final release of Quarkus. It will be in the next week or so, right? So all these functionality is still considered like beta. The first public release was in March. It was Quarkus 11. And now we are approaching 1.0. So we will release Quarkus 1.0 like in the next week or something. Why I'm saying this? Up until now, it was a little bit of, well, you know, let's add as much as we can. We would accept some of these extensions were developed by us, actually most of them, by the Quarkus team. Some of them were contributed by the community. And we would welcome everything because we want to grow. But now when we are approaching the first 1.0 release, we really start to care about the quality, and there will be a notion of Quarkus platform, which is a set of extensions that we promote as a set that target the main use cases that Quarkus is supposed to address. And for those extensions, actually most of these that I showed right now will be there. And they will definitely work both in native mode and the JVM. So things like Hibernate, well, if you don't support Hibernate, like, what are we talking about really, right? So these are really the key technologies. They will always be there and enabled. But there will also be a general Quarkus extension ecosystem that will include various things. And so if you guys want to, for example, develop your own extensions, you could do it. Then we could register it on our website, and our tooling will pick it up, and it will be discoverable by others and maybe used by others. But maybe you will not want to support native mode because it might be very painful for you to do all that. So we will have a different grading of filters just meet your requirements. So you could easily see what's supported and what not. So it's not like there are extensions, I will add them, and then I build a native image, so it doesn't work. So it's a bad experience, definitely. So yeah, we will try to make it evident for you, so when you use extensions, you can be sure that they work in both native and the JVM mode.
Okay, thank you. And one more, if you don't mind.
Yeah.
So you just mentioned there will be upcoming first version, or like, yeah. So should we expect big changes in APIs, like if I start building applications on the current version?
Not really. Not really. Well, first of all, you will not have to wait long, right? So it will really be like in the next 10 days, or maybe a week. And then, well, I can tell you right now, well, imagine you're a developer and you're approaching a release like in 1 week or a few days. Would you do drastic changes to the API? Well, probably not. So we're really now careful about making major changes. It's basically we are stabilizing things and addressing really the key issues. Yeah.
Okay, thank you.
Yeah, you're welcome. Okay. All right, thank you very much.